Hi class. So as mentioned via Google Classroom, I'm sick and I don't want to infect you, but that won't stop us from learning, so I'm recording this video. Alright, let's review quickly the lesson from last week. Again, there are special types of processes for ideal gas. So all of these three conditions have to be true in order to use these equations. So the first is it should be non-flow, and the process should be reversible, and of course the gas should be an ideal gas. The first process is isobaric, or constant volume. Since the volume is constant, so remember that the equation for the work is negative P dV. If the volume is constant, then dV is 0. You can also use these equations for the heat capacity. We have delta U equal to CV dt and delta H equal to CP dt. Okay, so since work is 0, then the equation for closed processes, delta U equal to Q plus W, the work there is 0, that's why delta U equal to Q. The next process is isobaric, which means constant pressure. Again, you can use these equations for heat capacity, and remember, for isobaric processes, delta H equals Q. And for this process, if we want to solve for work, simply transpose Q to the other side of the equation to isolate W. And the next type of process is isothermal process. In an isothermal process, we can make use of these equations Cp dt and Cv dt. But since it's an isothermal process, meaning the temperature is constant, then the term dt is 0. That's why both delta U and delta H is 0 for this type of process. If that's the case, then our equation delta U equal to Q plus W, delta U would be 0. That's why Q will just be equal to the negative of W. Okay? And then we can make use of the ideal gas equation to derive this equation. So remember that we derived this last week. It's from the equation negative P dV, and we just replaced P with its equivalent in the ideal gas equation, and we took the integral. Okay, and the third type of process is an adiabatic process. In an adiabatic process, Q is 0, there's no heat transfer. If that's the case, then delta U will be equal to W, and it's still equal to CV dt. Delta H is still equal to CP dt. And I told you to study the derivation on your own. So for an adiabatic process, these equations would be true. Now we have the term gamma, which means Cp over Cv, and also for an ideal gas, Cp minus Cv equals R. Okay, and then we also have the equation for work for an adiabatic process. So this is the equation for work. Alright, now we have values for gamma depending on the type of gas. So we have monoatomic gas, that's 1.67, diatomic gas 1.4, and triatomic gas 1.3. Lastly, we have a polytropic process. So in this case, there's no specific condition other than reversibility, and these equations would be true. Okay, so this delta U CPDT delta H equal to CPDT would be true, and the definition for work for reversible processes and the energy balance for non-flow closed system. And we can generalize equations for polytropic process using these equations, which is similar or in parallel with the equations of an adiabatic process, but instead of gamma, we use delta. But so we can also make use of this work and Q equations. And then this last slide will show that actually if we replace delta with certain values, we get the equations for each type of special process. For example, if delta is 0, so meaning we substitute 0 here, so that means P would be constant and we would get the equations for isobaric. And you can do that for the rest of the equations to derive the equations for an isobaric process. For isothermal, just replace delta with 1. For adiabatic, replace it with gamma. Isochoric, infinity. So we can derive the different equations for the special processes from these general equations of polytropic processes. So let's answer this example. The conditions would be non-flow, reversible, ideal gas. So 100 moles of an ideal gas with a given Cp 5 halves R and Cv 3 halves R is changed from 1 bar and 12 meter cube to 12 bars and 1 meter cube by the following mechanically reversible processes. Okay. So different processes, and we need to solve that one by one, and we need to calculate these values or these parameters for each of these processes. Let me catch my breath. Okay, let's draw the problem first. Okay, let's assume that this is the closed vessel which contains our ideal gas. Oops. So we have 1 bar and 12 meter cube. P1 equal to 1 bar, V1 equal to, so this, the first state would be called state 1 and the second state would be state 2. P2 V2. Okay. The first The first process is isothermal process, isothermal compression. So the temperature is constant. Okay, so this is 100 moles of ideal gas. Remember that for isothermal processes, what is true? Isothermal processes, delta U equal to delta H equal to 0 because dt is 0. So this is true. Therefore, our equation is this one. We can use this equation for Q and W. So for this one, delta U delta H is 0. Okay. And then we make use of the equation to solve for Q and W. Okay, let's plug in the values. So the given is so we need to find a value of RT. Okay, but remember that PV equal to nRT. PV equal to nRT, and if the volume is expressed as molar volume, it's actually PV equal to RT. So in the equation here, we can substitute PV. Okay, so let's do that. PV ln V2 over V1. Or we can make use of this equation. PV ln P1 over P2. So either equation would be true. So either in terms of V or in terms of P. Okay. Let's substitute the values. So P is 1 bar, and that is 1 bar is 1 times 10 to the 5 Newton per meter squared. Just look at this part of the screen. Times the, so that is times the volume 12 meter cube, okay, times ln P1 over P2. P1 is 1 bar, so here the units don't matter because it will be cancelled. P2 is 12 bars. So we can use bars or pascals or Newton per meter squared, doesn't matter. The units will cancel. Here the unit meter squared and will cancel, leaving 1 meter in the numerator, so that would be 1 Newton meter, which is equal to joules. Okay. Solving this problem, we'll get for Q, okay, Q equal to negative 2982 kilojoules, and then W equal to 2982 kilojoules. Okay, since Q is equal to negative W. Okay, let me copy paste that. Okay, so we're done with the first process, the isothermal process. Let's go to the next process. What's the next process? The next process is adiabatic compression followed by cooling at constant pressure. Okay. So by the way, did you notice anything about the temperature? What do you think would be the temperature at here and at the second state? Since it's an ideal gas, okay, so let's go back to the PV over T is a constant for an ideal gas. Okay, so the PV P1 P1 oops T1 V1 equal to P2. Okay, since our P1 is 1 meter cube, 1 bar, and B1 is 12 meter cube, our P2 is 12 bars. So let's replace that. This is 1 bar, this is 12 meter cube. We don't know T2. P2 is 12 bars. V2 is 1 meter cube. What do you think would be T1 and T2? T1 is just equal to T2. And this is true for all of the throughout the problem. For ABC, T1 is just equal to T2. Meaning, delta U equal to delta H equal to 0 would be true throughout the problem. Okay, because T is constant. Okay? But what does it mean in the second problem? What does cooling mean? Okay, so it just means that Q is transferred. Okay, not necessarily there's a change in the temperature. Okay, excuse me for a while. So it doesn't necessarily mean that there's a change in temperature, but there is a heat flow. Okay, so let's solve the problem. adiabatic compression. From P1 we reach P2. Okay. And since the first step is adiabatic compression, P1 to P2, but we don't know the volume here, so let's put an intermediate volume here, Vi, and then followed by cooling. So here the first step is compression, and then the second step is cooling at constant pressure. So pressure here, P2, is just equal to the final pressure, P2, equal to 12 bars. Okay? Paabot nga ng electric fan, please. Since this is an adiabatic process, the first step, we can solve for gamma. So gamma is, equal to Cp over Cv, and this is equal to, what's the given? It's the given gamma, Cp. So that's 5 halves over 3 halves. 5 halves divided by 3 halves. That would be 5/3, right? Okay. So the first step would be adiabatic compression. Let's calculate for the intermediate volume. We may use the equations for adiabatic processes. Okay, so we make use of this equation since we know P1, V1, and then P2. But since we're dealing with an intermediate volume, this would be Vi. So let me write that for you. P1, V1, okay, raised to gamma equal to P2, V2, Vi raised to gamma. Okay? Okay, so again, why is it Vi? It's Vi because there's an intermediate volume before step 2. Okay, but we know that P2 here in the intermediate step, so this is the intermediate step because there are 2 steps, right? Compression, then cooling. So we know that P2 is already equal to the final pressure since the second step stated that step 2 is at constant pressure. Okay, so let's solve for V intermediate. Rearranging the expression to isolate Vi, this is just equal to V1 P1 over P2 raised to okay, V1 should be raised to gamma. Okay. But then, everything here should be raised to 1 over gamma. Okay. Raised to 1. Okay, so that's why this would be VI the gamma here would cancel out. So that means only this term or expression P1 over P2 would be raised to gamma. Substituting the values, we have again, doesn't matter what unit we use here because the units will cancel out for pressure. This would be 1 over 5/3, or that would be 3/5. The reciprocal of 5 over 3 is 3/5. And we'll get 2.702 around this value. Okay? So that's the intermediate volume. We're not finished yet because we're still here at step 1. So we just solve VI. Next, we must solve the work. Okay. So we must solve the work from step 1 to step 2. So we make use of this equation. We'll make use of this equation to solve the work. Okay. And as you can see here, we won't use VI yet, okay? Because in the equation, it's just V1. There's no second V or V2, or in our case, V intermediate. So we just plug in. Okay, we plug in the values. I won't write it anymore. Okay, just plug in the values for P1, V1, P2, P2, and P1, and gamma. The work here in step 1 would be equal to 3060 kilojoules. Okay, and then next we solve. Okay, we solve for work during step 2. Okay, so during step 2, what is the equation of work? Since this is an isobaric process, constant pressure, we can make use of the general equation for work, which is not included here, but its work is negative PdV. Okay, so integrating that is just P equal to delta V. Okay, so this is just P dV. Integral, oh no, I don't know how to, yeah, integral of negative P dV. So that's negative, so this is equal to negative P V2 minus V. Should it be V1? It shouldn't be V1, it should be V intermediate. Because we are just solving for step 2. So from VI to V2. Okay, so it should be V intermediate. So we know the value of V intermediate from our previous equation. So that's negative. By the way, this should be P2. Okay, P2, constant pressure. So P2 is 12 times 10 to the 5 Newton per meter squared. Newton per meter squared. And then V2 is 1 meter cube minus VI. We solved this earlier. 1 meter cube. So the meter squared will cancel, leaving the unit Newton meter or joules, and you will get positive 2402 kilojoules. Okay, so this is step 2 work. Okay, so this is step 1. Step 1 and step 2. Step 1, step 2. So let's put a line here to delineate. Okay, what would be our Q? So by the way, what is Q in step 1? Since it's an adiabatic process, Q is 0 in step 1. How about Q in step 2? What is Q? It's delta U minus Q. Okay, and delta U is 0. Okay, so that means Q is no, we don't know. We don't know yet Q for step 2. Okay, so let's just leave it as is. Okay, so there might be an intermediate temperature here, so we are not sure with that, but we know that for T1 is equal to T2. So let's leave that. Let's leave Q unknown first. Okay, let's leave Q unknown first. First, we solve for the total W. Okay. So what is the total work? The total work is the work in step 1, work total. work in step 1 plus work in step 2, and that is equal to 3063 plus 2042 equal to 5106 kilojoules. So that's the total work. Okay. The question is, what would be the total Q, okay, for step 1 and step from state 1 to state 2. Okay. Since we know that from state 1 to state 2, T is constant, so delta U is 0 from state 1 to state 2. So this one is the intermediate step. If that's the case, if delta U is 0, then Q is just negative W is negative 5106 kilojoules. Okay? Negative 5106 kilojoules for the total. So that's the answer. Okay. The next, how many minutes are we in the recording? You can see it. Okay, the next process is adiabatic compression followed by cooling at constant volume. Okay, so let's draw the problem. Let's just copy paste. Okay. Adiabatic compression followed by cooling at constant volume. So we know that the intermediate pressure is 1 meter cube because cooling at step 2 is constant volume. So this two should be equal. But we don't know the intermediate pressure. So let's put an intermediate pressure here. Okay. So 1 minute break. The same with the previous problem. We need to calculate the intermediate pressure first using the equations for adiabatic process. So let's go back to the equations of adiabatic process. So we still use the same relationship, okay? But this time, V intermediate is unknown. Okay. So from here, derive the equation for the intermediate pressure. Let's do that. Okay, I will skip the derivation, but it's very easy. Just do what we did from the past problem, the last part of the problem. So that is V1 over V2 raised to gamma. Okay, so okay, so this is how we solve for the intermediate pressure. Plug in the values. P1 is 1 bar, so that's 1 times 10 to the 5 Newton per meter squared. V1 over V2. So that is 12 1 raised to gamma. Okay, raised to gamma. The units will cancel out and we'll get, so it doesn't matter actually what unit we use for pressure. So let me just convert that. Instead of Newton meters, let's just use bars. 1 bar. 62.898 bars. Okay. So that is P intermediate for step 1. The same equation that we used for work, okay, we plug in all the values. So we have P1, V1, and then for P2 we use the intermediate pressure. Okay, to get the work. Okay, so plugging in, I will not anymore show that step by step. Just plug in the values, and for P2 use the intermediate pressure that we solved here. Okay, the work that we'll get would be 7635 kilojoules. Okay, so that is the work. So using this equation, so just use okay. For step 2, what is work? What is work for step 2? Since V2 is constant from the intermediate step to step 2, V is constant, then work is 0. What would be the total work? Work total equal to work 1 plus work 2, but since work 2 is 0, then this is just equal to 7635 kilojoules. And then just like the previous problem, since temperature is constant from state 1 to state 2, okay, delta U is 0 from state 1 to state 2. Q is just negative work equal to negative. Okay. Next. Letter D. Letter D is heating at constant volume followed by cooling at constant pressure. Okay, let's draw heating at constant volume. So V2 is 12 since the intermediate volume is equal to V1. 12. So this should be equal to V1, 12 meter cube. Heating at constant volume followed by cooling at constant pressure. Okay, so this should be P2 because step 2 is constant pressure. So step 1 is constant volume, step 2 is constant pressure. So that's why the V intermediate is equal to V1, but the P intermediate is equal to P2. Okay? So what is work during step 1? Let's go back to our slides. So step 1 is an isobaric process. Obviously, work is 0 in step 1. Work is 0. Okay? Because volume is constant. And then Q is equal to CV dt. Okay? So we can make use of that, or we can just solve that later and proceed to the work in step 2. Step 2 work is, so it's for an isobaric process, it's negative PDV. Okay, negative PDV. Again, we plug in the values. Okay, let's work is negative P dV integral. So that's P2 negative V2 minus V1. Okay, plugging in the values. P2 is 12 10 to the 5 Newton per meter squared, and V2 is 1, V1 is 12 meter cube. Meter squared will cancel, so we'll get 13,200 kilojoules. Okay, and that is the work for step 2. That's the work for step 2. Okay. So let's solve. So a shortcut to solve for Q would be, let's solve for W total first. So that's W1 plus W2. And since W1 is 0, so that's just equal to 13,200 kilojoules. Since state 1 and state 2 would have constant temperature, that means delta U is 0. So from state 1 to state 2, delta U is 0. Q is equal to negative W equal to negative kilojoules. Okay, but we can actually solve for Q in each step using for step 1, we can make use of this equation, Q equal to CV dt. And then for step 2, Q is Cp dt. And just add the 2 to get the same answer here, negative. So we can write that. Q is Cp dt for step 2. Step 1, Q is Cv dt. So either way, I will get the same answer. You can try it. So just add Q1 and Q2 to get the total Q. Okay? But the problem is, we don't know, okay, how, so dt here would not be T2, okay, because if that's the case, dt would just be 0. So there must be an intermediate temperature here, which you need to solve. That's the problem. You still need to solve for an intermediate temperature. To be able to solve for Q in step 1 and Q in step 2. So you need to get Ti. So dt here would be T1 to Ti. dt here would be from Ti to T2. Okay. So the shortcut would be, since we know that delta U is 0 from state 1 to state 2, just get the negative of W, right, to solve for Q. This is tiring. Lastly, letter E. This is letter E. Cooling at constant pressure followed by heating at constant volume. It's the opposite. Oops. It's the opposite. So first is constant pressure. So this is 1 bar. And then step 2 is constant volume. Okay, so it's just the opposite of the first problem. So we do the same. So at the first step, we make use of PDV, negative PDV. Okay, and you'll get the first step here, just PDV. And the second step, work is 0. Okay, work is 0. So the total work is, and for Q, okay, so just do the same. Okay, it's been an hour, so let's stop here. Anyway, the problem is solved. If you have questions, unfortunately I can't meet you right now. I'm very much sick right now, so just send your questions via email. Okay, have a nice day. Bye.